Graphing rational functions is easiest if you break down certain parts of the function, and more specifically you're looking at vertical and horizontal asymptotes, intercepts. Once in a while you're going to have an oblique asymptote. So to start with, the vertical asymptotes, you would take the bottom and set it equal to 0. So b of x is equal to 0, and where this does occur at 0, that means that the bottom is equal to 0. That makes this undefined. Therefore, that x cannot be and it part of the graph, and therefore the vertical asymptote would be at that x. Then you can go to horizontal asymptotes. Horizontal asymptotes have three cases, and you're looking at the exponent on the top and the exponent on the bottom. Where the exponent on the top is less than the exponent on the bottom, that means that the top is going to grow less than the bottom. And when it grows less than the bottom, it means the bottom is going to grow faster and outstrip the top, which means it's going to go towards 0, the whole thing towards 0, because a smaller number over a bigger number, as you go to infinity, is eventually going to get equal to 0, and therefore your horizontal asymptote would be y equals 0. The second case is where the exponents are equal. Where they're equal, it means they're going to grow at the same rate. Therefore, you're looking at the ratio of these leading coefficients. If you had this case where exponents are the same, leading coefficients is 2 over 3, the horizontal asymptote is y equals 2 over 3. And in the third case, where n is greater than m, such as this case, you're going to see that there is no horizontal asymptote. Intercepts you can figure out in two different ways. To find the y-intercept, you put 0 in for x, and to find the x-intercept, you can put 0 in for y, and then evaluate what those two are. That's the easiest way. The third asymptote is an oblique asymptote, and this occurs where the leading exponent on the top is one more than the leading exponent on the bottom, such as what you see here. And where you have the 2 is one more than 1, you're going to have a dashed asymptote, and therefore the graph is going to be wedged between the vertical asymptote and that oblique or slant asymptote. One thing you have to do here, however, is to divide the bottom by the top, or I'm sorry, the top by the bottom, and when you do that, you're going to figure out what your oblique asymptote actually equals. We'll do an example a little bit later. Looking at this equation, notice vertical asymptote is where the bottom equals 0, so you're going to have x equals -2. Here, looking at the exponents on top and bottom, they're equal, so you would say the ratio of the coefficients, 6 over 1, y equals 6 is the horizontal asymptote. Again, looking at the exponents here, 1 is equal to 1, which tells you that it's going to be the ratio. The horizontal asymptote is the ratio of the coefficients, which is really going to be 2. Therefore, at y equals 2, that's going to be your horizontal asymptote. Vertical asymptote, y equals -3. I want to look at a more specific example. F of x equals x squared plus 1, all divided by x minus 2. The first thing you're going to recognize is that the leading exponent on the top, 2, is 1 more than the leading exponent on the bottom, 1, and therefore you have to divide this out to see what the slant asymptote looks like. As I divided it out, you can see that it's written as f of x is equal to x plus 2 plus a little bit, and as you can see x go to positive or negative infinity, this is going to be 0, which means it's a little bit more than this or less than this, but it'll never be that. It'll always be adding something or subtracting something. Therefore, that will never occur. The graph can never occur on that slant asymptote. Looking at the vertical asymptote here is going to be where the bottom equals 0. When you solve for that, you get 2 is equal to x. The horizontal asymptote, you're comparing these. That means that actually it doesn't exist because the the exponent on the top is one more than the bottom, and you're going to have an oblique asymptote. The oblique asymptote is going to be where y is equal to x plus 2, and that's what I've drawn there. Intercepts. Intercepts are going to be putting 0 in for x. When you put 0 in for x, what do you get? Negative 1/2. 0 in for y is where the y is equal to 0. That means that the top has got to be equal to 0, which it never can happen. So that's our only point, which means that that point's going to be down here. Of course, always labeling points on the graph. Domain, are there any restrictions? Yes, x cannot equal 2. So all real numbers, x cannot equal 2. Now, when you graph this, you know that the graph has got to go through this point right here. And you also know that the vertical asymptote is where x is equal to 2, which means that you are going to have some sort of a vertical asymptote out here. Meaning you're going to have the graph eventually approach these two lines as you graph it. And so more or less you're looking at a graph that looks like this, not intersecting those asymptotes. And then what you're going to have is another graph up here. Because this is to the first power, it's going to have opposite behavior. So this is going to go to negative infinity. This is going to go to positive infinity up here, which means that you now are going to have part of the graph up in that area. If the bottom had an even exponent here, you would know that it's going to have the same behavior. So it would be the similar section on the graph, but on the flip side. That concludes graphing rational functions, looking at the horizontal and vertical asymptotes as well as the oblique asymptotes, x and y intercepts.